Hey Ramblers! This video covers section 1.5 in our textbook and deals with the second half of that section, which is inverse trig functions. Now we've been dealing with inverse functions ever since you started looking at functions. For instance, when you considered y equals x squared, the inverse function of that would be y equals the square root of x. So these are not terribly new concepts to us, though because of some of the restrictions and our discomfort with trig in general, they are a little scarier. So the purpose of this video is to introduce you to arcsine and arctangent specifically, because this book deals with those two functions most often. But I want you to know there is an arccosine and arcsecant and arccosecant, etc., etc. But we will just focus mostly on those two. And then we also want to take a look at the graphs of these functions, because as you'll see, arcsine, arccosine, and arctangent have a pretty restricted domain. And we want to look at why that is, just to help to demystify it. All right, Ramblers, thanks for watching, and I hope this helps.
Sometimes we need to know a number that has a given sign, or a number that has a given tangent. For example, you might want to solve the equation, the sine of x equals root 2 over 2. Now that's a pretty simple one, and one that we might know just from memorizing our first quadrant trig values. But let's go through it algebraically. So if I wanted to isolate x, I would have to undo this sine function here, because x isn't by itself. It's not being multiplied by sine, because then I would just divide. But x is inside the sine function. So to both sides of the equation, I have to take the opposite of the sine function, which is called the arcsine function. And you can write it out, arcsine, as I have in the title, or you can notate it as sine to the negative 1. Now let's talk about that notation in a minute, after we solve this. So if I take the arcsine of both sides, the sine and arcsine will cancel each other out, just as square rooting and squaring cancel each other out, or multiplying and dividing. And so on the left side, I'm left with x. And on the right side, I'm left with the arcsine of root 2 over 2. And we'd have to go to a table, back in the old days, or you would just type that into your calculator, being sure to be in radian mode. And when you did that, you would get that x equals pi over 4, which is, of course, true. Now suppose we were going to try something a little more complicated. We would solve this the same way we did with any other kind of equation. We're going to run PEMDAS backwards. So the first thing I'm going to undo is that subtraction by 3 as I try to isolate my x. Then the next thing will be to divide through by 8. And then in this step, this is where we hit the need for the arcsine. So in order to extract the x from the inside of the sine function, I take the arcsine of both sides. On the left, I'll get the arcsine of 1/2. And then on the right, the arcsine function and the sine function are inverses. So I'm just left with 2x plus 1. On the left side, the arcsine of 1/2 means what angle has a sine that is 1/2. And as you begin to review your first quadrant trig functions, that of course is pi over 6, or since we want to be in that's pi over 6, which is what we want in radians, but you might recognize that as 30 degrees. So that's equal to 2x plus 1. Now it solves just like any other algebraic equation. I'm going to subtract 1/2 from both sides and divide by 2 to isolate x. This gives you your final answer of negative 0.2382. And with trig functions and inverse trig functions, let's go out to 4 decimal places. That's kind of the norm. All right, let's take a look at the graphs of, arccosine, arctangent. They all work the same way. But let's take a look at the graphs of these functions to understand why we have the limitations on the domains. Let's take a look at the graph of y equals sine x. Probably very familiar to us now after the last section. You can see that I've shown just 2 periods, although it's infinite in both directions. And if we consider the vertical line test, we would know that any vertical line would just cross sine at one place, which means sine is a function. But how about the horizontal line test? What was that a test for? If a function passed the horizontal line test, it meant that the function had an inverse. Clearly, if we drew a horizontal line anywhere on this graph, it would fail multiple times, and we're just looking at two periods. So the graph of sine x is not invertible unless we restrict the domain on its inverse, and that's what they do. Now let's take a look at another image of sine, and I'm going to overlay it with an image of arcsine. So this image kind of expands the x-axis. So now we're looking at a much wider image so that we could get a little better or a less steep angle on the line y equals x. Well, as you can see, sine is in black, and arcsine would be the dotted line, which becomes red. And the reason it becomes red is that is the reflection of the sine curve from negative pi over 2 to pi over 2. And when we reflect that part of sine, we get this red image on arcsine. And the reason we chose that portion of the sine graph was so that it would now pass the horizontal line test. And the inverse of sine, arcsine, would in fact be a function that would not have multiple values. Okay, that's why we get this goofy definition for arcsine as being defined from negative pi over 2 to pi over 2. Let's take a quick look at tangent and arctangent, and you'll see that the same thing is going on there too. Let's take a look at the graph of tangent. Just with sine and cosine, tangent is also periodic. So if we were to draw a horizontal line across the tangent function, it would hit a value on the tangent function every pi, because pi is the period. So that means that we have to restrict the domain of tangent if we're going to look at its inverse. So let's do that. If I look at just that central part of the tangent graph, spreading from negative pi over 2 to positive pi over 2, and I reflect that portion over the line y equals x, I do get an inverse that is a function, stretching all the way from negative infinity to positive infinity. So there's no restrictions on the domain of arctangent, just we have to restrict the domain of tangent in order to generate arctangent. Okay, Ramblers, from here we're going to move on to the exercises. Thanks very much for watching. I hope this helps. Please excuse that we're not looking into arc cosine, but it is very similar to sine, and it just doesn't come up very often in this book as much as these two functions. So thanks for watching. I hope this helped.